Hello everyone, my name is José Lucas Otero Couto and I will be presenting the results of an experimental process made in cooperation with the colleagues Dr. Cibele Viana and Edilson Teixeira, titled Slugs of the Itaparica Tradition, an experimental approach to the GOJA01 collection. Enjoy! The Itaparica tradition is an archaeological culture that flourished in the Pleistocene-Holocene transition and early Holocene in Brazil. For some context, I will be taking you all to a little trip down to the Central Brazil Plateau. The Central Brazil Plateau is composed mostly by the Cerrado biome, a vast tropical savanna-like ecosystem that covers around 20% of Brazil's total land area. It is characterized by a unique combination of grasslands, shrublands, and riparian forests that have adapted to the region's distinct dry climatic conditions. During the Pleistocene-Holocene transition period, the Cerrado biome was quite different from what it is today. It is believed that the climate was wetter and cooler, with a higher frequency of rainfall, resulting in a denser and more extensive forest cover, with more abundant and diverse fauna and flora, including some megafauna species. The focus of this presentation, the GOJA01 site, is located in the southwest region of the state of Goiás, and is part of an important archaeological region denominated the Serranópolis Archaeological Complex. The first researches carried out in Serranópolis were coordinated by the priest and archaeologist Pedro Inácio Schmitz in the 70s and continued until the 90s. That effort located 53 sites. Of those, 27 sites, mostly located on rock shelters adorned with pictographs and petroglyphs, were excavated, producing a large collection composed of ceramic, osteological, and lithic artifacts, being the latter part the vast majority of the collection. Only in recent years, new excavations have been done, coordinated by Professor Júlio Rubin. The GOJA01 is one of the most important rock shelter sites in the region and was extensively excavated. The interventions covered 40 square meters and reached depths of up to 2 meters. Schmitz described a consistent pattern of occupational horizons throughout the sites, containing the Itaparica, Serranópolis, and Una archaeological traditions. More than 40,000 lithic artifacts were found at the site, of which 517 were instruments. The Itaparica tradition is marked by the persistence of a specific kind of instrument, the slugs, that are a kind of plano-convex scraper that can be found on various shapes and sizes, and is mostly made of good quality silicified sandstone. We agree that the techno-functional analysis is a good way to approach the complexity of variants we can find on this kind of instrument, as Antoine Lourdeau demonstrated when he described the Itaparica Techno-Complex in 2014. In this manner, we can describe an instrument as a slug observing parameters such as a plano-convex structure, a flat ventral surface, a transformative unity usually placed on the distal portion of the tool, a convex dorsal surface, and a prehensive unity usually placed on the proximal portion of the tool. So why are they called slugs? Well, see for yourself. These instruments have been referred to as slugs since the 70s for their resemblance to the invertebrate. And in the present days, it's a dear term for the Brazilian archaeologists. So having this background being laid out, we decided to develop an experimental process based on the collection from the GOJA01 site that will recreate a plausible operational manufacturing chain of these particular instruments, aiming to understand the inherent functional intentions and production steps associated with such artifacts. The main objectives of this research will be the reproduction of 10 slugs and subsequent handling of these tools in proposed activities. From these experiments, we aim to contribute with a practical approach to the analysis and comprehensions of the slugs. We divided the research in 4 steps. Step 1. Selection of the slugs to be reproduced and subsequent compilation of techno-functional analysis of each instrument. Step 2. Field activities divided into 2 points: selection and collection of analogous raw materials, selection and collection of hammerstones. Step 3. Knapping activities carried out in the laboratory divided into 3 points: formatting of the cores and debiting of support flakes, production of the instruments by façonnage, installation of the transformative unities. Step 4. Employment of the produced replicas in a task. The proposed task is the scraping of impurities from a fresh leather to prepare it for conservation. Right off, we were confronted with the challenge to choose a varied selection of archaeological slugs that would be relevant and representative of the collection. So we sought to obtain the sample based on our selection on parameters used by Lourdeau in 2014 to classify different technotypes of slugs. By choosing different configurations of slugs, we could have the opportunity to reproduce various technical structures that make up this type of instrument. The chosen pieces were based on the combination of 3 parameters: the depth of edge exploration, shape of midsection, and shape of the distal transformative unity, as you can see on the chart on the right. After the selection of the artifacts, we made a compilation of the techno-functional analysis of each slug to serve as reference material for the experimental process. After that, we organized a field trip to the Serranópolis region with the goal of finding sources of raw materials. Everything went very well, and here you can see a group of archaeologists facing the harsh reality. This block was found around 2.5 kilometers from the car. Here's our party in another location. Some say this rock formation resembles a camel, but I'm not going to be the one to associate another rock to an animal shape in this presentation. And finally, the result of a very successful field trip. We can see various blocks of different silicified sandstone sources and a box full of hammerstones. Now that we had the necessary raw materials, we prepared ourselves for the debiting of support flakes. Taking into account the absence of cores into the archaeological collection, it was incumbent upon the experimental archaeologists to devise a core exploration technique that would enable the exploitation of useful volumes from the blocks of raw material. Our planning led us to the conclusion that to be suitable for providing support flakes for the elaboration of slugs, a core should possess a well-designed percussion plan and a chipping surface with guide ridges associated with a substantial reserve of high-quality raw material for knapping. From a discussion that involved a dialogue between the mental image projected in the minds of contemporary flint knappers and previously known knapping techniques, we decided to apply 2 basic gestures related to the detachment of support flakes from the core: the direct internal and the tangential, as depicted in the scheme on the right. We used basalt hammerstones of various sizes to accomplish the task. Here you can see an example of a direct internal gesture applied. After some consideration, we can say that in our experimentation, the blocks underwent debitage classified as C and D laminar. In both cases, following the ridges was a recurring theme, with the type C core ridges being based on natural occurrences on the raw material, requiring little technical investment for their exploitation. However, the D-laminar type required greater mental planning and technical effort, as partial formation of the core structure was necessary. A total of 34 support flakes were produced. Upon selecting which ones were suitable for reproducing the archaeological instruments, we observed that not all instruments could be produced from supports obtained by the tangential gesture. Similarly, not all instruments could be produced from supports obtained by the direct internal one, demonstrating that both techniques are valid and complementary when it comes to obtaining support for the production of slugs. From those 34 support flakes, 13 had the potential structures to reproduce a slug from the reference collection, and were selected and analyzed. After that step, we were ready for the façonnage process, where the entire artificially constructed operational chain culminated in the production of replicas that demonstrated technological coherence with the reference archaeological instruments. The production of these replicas reaffirmed the deep relationship the slugs share with their support flakes. It was observed that when a support flake possessed all the desired structural characteristics, the façonnage process primarily involved simple unifacial flaking and not a lot of mental preparation. So when contrasting the façonnage process with the débitage one, it can be asserted that the latter required greater mental investment. The former, on the other hand, proved to be surprisingly straightforward and effective. From the 13 selected support flakes, we produced 8 replicas, of which 6 we considered successful, reproducing functional structures similar to those of the reference slugs. On the right, we can see an example of one of the replicas produced with all the façonnage flakes associated with the process. For the final step, the using of the replicas, we started to remove the skin of a ship using a chosen replica. We utilized the transformative unity in a vertical motion, making parallel strokes similar to how one would use a knife. This tool worked efficiently, allowing us to detach around 30% of the animal's skin. However, we ceased using it due to the blade's edge showing signs of wear. Instead, we opted to utilize an untouched support flake and employed it in the same manner as the previous two. We saw as the flake tool was resharpened by some light peripheral unifacial napping that it took the shape of a slug, and on the 4th resharpening process, the flake tool broke and we decided to select one of the fragments to create a smaller tool that could be used in hard-to-reach areas. Once the skin was entirely detached from the carcass, we stretched it by securing it onto a thick vine frame with ropes. The process of removing the impurities of the skin was initiated by testing various movements in order to comprehend which gesture would allow for the most efficient use of the tool. Through several trials, we arrived at a technique where the slug is held in an inverted manner, with the distal transformative unity facing downward, the prehensive unity facing upward, the ventral surface in contact with the skin, and the dorsal surface in contact with the palm of the hand, as you can see on the video. The second technique employed was developed by applying cutting movements in both directions, while holding the membranes being cut with the other hand. To maintain the sharpness of the tool, we conducted various resharpening procedures by unifacial napping of the distal perimeter of the tool. We observed that the maximum sharpness of the slug tended to diminish after approximately 15 to 20 minutes of use. In the manner described, we were able to get rid of the vast majority of unwanted material present in the skin. Then we set it to the side and let it dry for 7 days. For the scraping of the hair, after drying the skin, we prepared the surface by placing a wooden log supported on another smaller log, forming an inclination of about 30 degrees. This way we created a surface to receive the dry skin that would be scraped, and the arrangement also served as a seat for the craftsman. We started the task by testing some scraping methods and came to the conclusion that the best way to hold the tool would be with the ventral surface of the instrument facing down and the dorsal surface in contact with the palm of the hand, as you can see on the video. We also conducted various resharpening procedures during this process and found that the sharpness of the tool took less time to degrade, around 10 minutes, when compared to the previous activity. We ended up with a rawhide material that could be used for various purposes. To conclude the presentation, here we have the life cycle of a slug created by this experimental process. Throughout the activities, we observed that the technical configurations of the slugs, combined with the unifacial flaking technique, confer a series of advantages to such instruments, like the recurrent possibility of easy reconfiguration and resharpening of the edges. The replica we used, for example, was resharpened 13 times. Well, ultimately, we were pleased to present a viable operational chain for the slugs, and without a doubt, we felt a much stronger connection with them. Thank you very much.